Welcome to our presentation, High Performance Historic Masonry Retrofits. We pride ourselves on providing critical knowledge and components to build high-performance buildings. Our company, 475, was actually founded out of working on several passive house historic masonry retrofits, so the topic is very close to us. Let's get started. So first, what is high performance in this context? First, from the user's perspective, the building should be comfortable for the occupants, have a healthy indoor environment, be energy efficient, whether hitting passive house or other low energy standards. It should be resilient, it needs to be affordable, and we treasure the aesthetics of the historic buildings and don't want to diminish them. On the other hand, we have high performance from the masonry's perspective. As Louis Kahn might have asked, what does the brick want? His simple response might have been, it wants to be dry, and it wants to be seen. So in historic masonry buildings, we have two wants in seeming conflict. Why in conflict? Because as we see on the left, a poorly insulated building, it is inefficient and uncomfortable. It is a radiator to the world. But this radiator effect is keeping the brick relatively warm and dry. On the right is a well-insulated building. It is energy efficient and comfortable, but this results in the wall being colder and wetter. And with the brick being wetter, we become concerned with freeze-thaw and mold damage threats. In looking at the threat of freeze-thaw destruction, it is important to recognize that it is a whole systems failure. Two things need to happen together. The masonry must be saturated, and the weather must be well below freezing for an extended period. So one question will be, how do we avoid freeze-thaw and still achieve high performance? We may not be able to control the outside temperatures, but we have a lot of control over preventing saturation of the brick. The preeminent building scientist Bill Rose has stated that freeze-thaw is not a temperature problem, it's an exposure problem, and it's in reducing the exposure where we'll focus. The other threat is mold growth. ASHRAE 160P is the basic criteria for mold growth propagation. When, on a 30-day running average, relative humidity is above 80% when the surface temperature is between 41 and 104 degrees Fahrenheit. So even if we successfully deal with the exposure issues and don't have a saturation and freeze-thaw problem, we need to be careful that the mold threat is mitigated too. To mitigate both threats of saturation and mold, we need to always be thinking about how we can increase the drying potential of the assembly. The basic formula for assemblies is also true for historic retrofits. It is that the drying capacity has to be greater than the unanticipated wetting. If you maintain this relationship, you'll have freedom from damage, structural damage, rot, and mold. So we have to always help the drying, and in doing so, we increase the resilience of these historic structures. Of course, we can avoid the problem altogether by simply insulating outboard of the masonry, putting it within the thermal envelope. The brick will be heated as part of the interior conditioned space. It's warm and dry. But while it's often preferable to wrap the exterior from a building science perspective, often we don't want to from an aesthetic perspective, and growing historic preservation districts often simply won't let us. So today we're assuming we can't wrap the exterior of the building. We're looking for robust solutions to make a high-performance building while insulating from the interior. In doing so, we ask the simple question, how do we avoid saturation and mold while maximizing comfort? There are 5 basic parts to the solution we will discuss today, followed by a walkthrough of real-world examples. First, as with any building, we must successfully shed water. Often, where freeze-thaw is detected, there is a breakdown in water management, and normal exposure is transformed into extreme exposure. Here are 2 examples. On the left, although it appears to be an abandoned building where all the brick gets to freezing temperatures, the brick is generally in good shape. Where the damage is occurring is where the downspout is broken and the brick is being flooded. On the right, we see damage below the windowsill. Here the sill is a rowlock of brick without strong flashing. The sill of a window will see the highest concentrations of water as the glass above isn't absorbing any water. These problems are avoidable. Make drainage function properly. Fix and restore, replace gutters, leaders, and drains. Move water away from the surface. repair and replace cornices, sills, flashings. Putting these basic building elements in good working order goes a long way to minimizing exposure and avoiding damages. To be sure we are shedding the water, we also need to verify the porosity and the quality of the brick. Even face brick meant for outside exposure can have a wide range of quality. Conduct a visual and physical inspection first. If there are concerns about porosity, we can do a variety of tests. Karsten tubes, a quick on-site absorption test readily available, shows how slowly or quickly brick absorbs water. If there are questions beyond this, full immersion saturation tests can be performed in the lab that are more scientific. We want to try to avoid coatings on the outside of the brick, but it may be necessary. We also need to repoint and replace masonry units as necessary. Use soft mortar mix. The mortar must be softer than the brick, as it is meant to be a sacrificial element. The New York City Landmarks Preservation Commission website has the recipe and lots of other great information on the subject. Let's look at a couple of water shedding failures that led to freeze-thaw damage. First, at a roof. This coping failure at the parapet is leading to saturation and freeze-thaw. But the freeze-thaw is not because of insulation. Parapets are always cold. Here, water shedding failure at the top of the wall is the result of a missing roof. It led to saturation and freeze-thaw damage. Consequently, when we see freeze-thaw damage at the tops of buildings, we can't assume it indicates a universal condition. Damages are usually localized. The rest of the brick below here is in okay shape. We see this in many masonry buildings that have been abandoned. The bricks are certainly freezing over the winters, but it is really, again, where we have faulty shedding of water, where we have overexposure, that the saturation and freeze-thaw becomes an issue. We also have to deal with rising damp. Masonry is a sponge for moisture from below. It can cause damage to the wood framing. Wet and dry cycling can lead to masonry damage with the uptake of ground salts. To combat this, we should provide interior and exterior drainage. We want to install water barriers. Depending on the physical circumstances, some of these approaches may not be feasible, but we do what we can when it seems warranted. In summary, for the first part, we spoke of shedding of water from above and below to avoid saturation, freeze-thaw, and other damages. Now, the second point of concern is airtightness and vapor control. Air control is more important than thermal control because it disproportionately affects 4 basic functions of the building. We need to be able to control the air quality, and the only way you really have control of the air is in an airtight environment. With greater control, the mechanical systems can be smaller while ensuring greater quality. Comfort. Drafts are the leading cause of discomfort, and then they need to be overcome with mechanical systems. Thermal bypass through air infiltration, convective loops, wind washing that degrade the insulation values by as much as a factor of 5, like a sweater without a windbreaker on a cold, windy day, and air-transported wetting. Air leaks and air-transported wetting are the biggest liability after bulk water, a much bigger liability to the enclosure than vapor diffusion. On the left is a classic Building Science Corporation diagram showing moisture loading through a 4x8 sheet of gypsum board over the course of a winter season. Vapor diffusion wets the enclosure with 1/3 of a quart of water, while a small air leak is carrying 30 quarts of water into the enclosure, an exponential difference. In historic masonry construction, we have ready-made points of air infiltration, such as where floor joists and beams are embedded in masonry walls. If we don't air seal, as shown on the diagram on the right, also by the Building Science Corporation, warm, humid interior air can move through the insulation, and we have a danger of condensation on the cold brick surfaces. On the left is physical evidence of this effect, where humid air circulated behind foam boards, which were intermittently adhered to the masonry, resulting in mold growth. So we want to surround our conditioned spaces with airtightness, the red line, and the airtightness must be continuous, accounting for penetrations and intersections. We want to surround our insulation with airtightness as well, as shown on the right, protecting it from degradation and maximizing the insulating potential. By surrounding the insulation with airtightness, we can easily gain insulating value without adding insulation, which takes away from interior square footage, always a concern in retrofits. For historic masonry walls, surrounding the insulation with airtightness means making the enclosure airtight inboard and outboard. The primary, most important air barrier is inboard of the main insulation layer, the red dotted line. This keeps the conditioned air in the conditioned space. The secondary air barrier is what we artfully call a windtight layer, and it really just needs to prevent wind from degrading the insulation value. The masonry wall, in some form, performs this role. To achieve a continuous air barrier, we have to pull everything away from the brick. Cut back 6 inches around flooring and ceilings so that we can see everything that we can get at the construction, especially where joist and beam ends are going into exterior and party walls. We need to fully expose the enclosure from the inside, examine, repair, and air seal. It's an opportunity to put back in good working order what hasn't been seen in decades and avoid liabilities down the road. We want to bring these historic buildings back into good working order. They've all too often been buried in poor renovations and neglected. The fundamental structure needs to be addressed. To make the brick windtight airtight, often repointing and fixing the brick can be enough. The best practice is to coat the inside face of the brick with lime plaster, which is vapor permeable and chemically helps fight mold growth. What we typically see installed is a permeable liquid membrane at the interior of the brick, as shown in the middle, like Stowe Gold or Emerald Coat. Again, the brick surface should not be the primary air control layer, as it is on the wrong side of the insulation. Put the primary airtight layer inboard of the insulation, keeping the conditioned humid air away from the cold surfaces, and thereby lowering condensation and mold damage risk. So what can we use for inboard airtightness? Drywall? Drywall is often used as an airtight layer. It's inboard of the insulation, so it's at the right location. But drywall is less than optimal for a number of reasons. It's exposed to occupants, so it takes abuse. It isn't continuous with the insulation. It's complicated. There are too many junctions and holes. And with the passing of seasons, it cracks and fails over time. The bottom line is that gypsum board is a sacrificial layer, and sacrificial layers should not be our control layers. What about spray foam for airtightness? Foam is problematic on many levels. It's full of dangerous toxic ingredients, very dangerous to the workers and potentially dangerous to the occupants. It is a fire accelerant. Industry standard formulations have high global warming potential, and it is difficult to remove or reverse. Of utmost importance is that installation problems are frequent, leading to unreliable performance. So overall, it's not an optimal approach. We are admittedly opinionated on the subject. Better options include sheathing and membranes. Sheathing like OSB or plywood are better approaches, but be warned, we have seen instances of leaky OSB out in the field, so you need to be careful with OSB. The INTELLO Plus membrane on the right, on the other hand, is specifically designed for the task at hand. It is robust. It is incredibly airtight. Next, we want to address vapor control. So here we have the classic images again. The poorly insulated building on the left, a radiator to the world, the warm wall bakes itself dry, and on the right, the well-insulated and comfortable building, which has a cold exterior wall. Cold things are wetter and stay wet longer. They don't want to dry. The only way they will dry is through vapor diffusion. So in terms of building drying reserves, keeping the drying capacity of the wall greater than unanticipated wetting, vapor diffusion is very important. So the trick is we want to prevent wetting but allow drying. In winter, when vapor drive is outward, we want to have an inboard vapor retarder, the red dashed line. But we don't want to put up a poly vapor barrier because we are air conditioning these buildings too. And in summer months, vapor drive from outside to inside could turn the wall assembly into a swimming pool. We need vapor variability inboard of the insulation to prevent wetting in winter and promote drying inward in the summer. We generally want to make the assembly vapor open to the exterior and vapor variable at the interior. The strongest vapor variable protection we can provide is a smart vapor retarder. This is a graph of INTELLO Plus, the most robust vapor variable retarder on the market today. It is almost vapor closed in dry conditions and becomes vapor open in wet conditions. Importantly, the membrane stays relatively retarding until it gets to about 65% relative humidity and then opens up as it begins to approach the danger zone of 80% for mold growth, allowing it to build the greatest drying reserves possible from season to season. Let's explain further. On the left is a section diagram illustrating the dynamic of preventing moisture loading in winter and allowing drying in summer. On the right, the diagram shows some specific numbers. On the winter diagram, the vapor drive going up and out, it shows if there is moisture in the assembly, it is pushing toward the roof, leaving the membrane at the driest location of the assembly, in this case 30% relative humidity. Inboard of the membrane is a very comfortable 50% relative humidity, as we have good airtightness. This results in an average humidity of 40% at the membrane and a strong vapor retarding position. On the summer diagram, the vapor drive is going down and in. Now moisture in the assembly is pushing against the membrane. The membrane is at the wettest location at 90% here, the canary in the coal mine, if you will. Inboard, we are showing a relative humidity of 70%, producing an average of 80%, and a membrane that is vapor open and allowing the assembly to dry inward. As this cycles through several years of seasons like a bouncing ball, we see that because INTELLO Plus is preventing wetting and allowing drying, the bright green line is bouncing downward, providing the largest drying potential and reserves against future unexpected wetting and the most robust moisture damage protection. With water shedding, airtightness, and vapor control dealt with, and exposure minimized, we now get the critically important question of just how much can we insulate. To examine different assembly insulation levels and compositions in different locations, we use WUFI Pro. WUFI is not an absolute guide. It helps tell us if we're improving or making worse a given situation, if the assembly is more risky or less risky. It shows that as we add insulation, we are adding risk. The question then is, can we see what might be boundaries of acceptable risk? What is a safe level of insulation? Let's look at some assemblies. Using the example of a 3-wythe brick building in Burlington, Vermont, with insulation and primary airtightness inboard. We want to see what the moisture levels are at the red dot, at the interior face of the brick, the point where mold damages are most likely to occur. For those new to WUFI, the graph shows relative humidity at the face of the brick in the green plotted line, with outside temperature in the red line over a 5-year period. We see the wetness in green peaking each winter and the temperature peaking each summer. The dashed green line represents the upper limit of 80% relative humidity we like to not cross, particularly when the temperature goes above the red dashed line at 41 degrees. This first simulation shown here is for fiberglass and airtight drywall, a typical builder's standard type construction. The brick is hitting saturation levels for extended periods in the colder months. Brick saturates at 96% under normal conditions and explains why the curve doesn't go higher. So this should be a disaster. And the question we ask is, why aren't these buildings failing all the time? The answer is that it's because they're leaking like sieves. They're still heating themselves dry. Next, let's look at 4 inches of cellulose without vapor control and same airtight drywall. The brick relative humidity is peaking at 96 degrees, but hitting saturation for a very short period of time. Yet it's always bouncing back to that point of saturation. It's never coming down. It's never really building drying reserves. There are still long stretches above 80% relative humidity and 41 degrees Fahrenheit, so there's still elevated risk. Now we add INTELLO Plus Smart Vapor Control and airtight membrane inboard of the cellulose. Starting at a relatively high moisture-loaded position, like the others, at 75%, over the course of a couple of years, the moisture levels bounce downward, keeping the brick out of the danger zone and practically eliminating the risk of mold growth. It is a more tolerant and more resilient assembly. We now have a safety buffer for unexpected wetting. So we know 4 inches of insulation isn't a problem, so then the question becomes, what's the risk tolerance of adding additional insulation? Here we're adding 2 more inches of cellulose, or 6 inches total. the relative humidity peaks grow stronger. The growing risk might mean that, to be absolutely sure, we want to limit insulation levels to something just short of 6 inches, 5 or 5.5 inches perhaps. But let's now go to 8 inches of cellulose and see what happens. And as expected, the risk level rises. And to 12 inches, we see it get more risky still. Again, WUFI helps tell us if we're helping or hindering the problem, a relative measure, not an absolute one. If you have a particular assembly that might be of a questionable risk profile, we are happy to follow up, sit down, or redo a WUFI of your assembly and talk about the results. So the question always gets boiled down to, how much is too much? And for walls, we see it be the very unsatisfying answer that it's highly dependent on situational specifics. We do want to note that with managed exposure, mold danger precedes freeze-thaw danger. And the key takeaway is that as insulation levels increase, the importance of airtightness and vapor control increase too. We can also note that windows should essentially be passive house compatible, about R6 installed. At the floor or grade, anything above R20 typically offers quickly diminishing returns. At the roof, we are largely unconstrained, and there are big benefits to lots of insulation, so we typically see R50 and above. The sky is the limit, as they say. Maximizing safe insulation levels also means making the insulation as continuous as possible, which means we must address thermal bridges. This image shows an example where there are floor slabs intersecting the exterior walls and are producing continuous thermal bridges. Masonry party walls are another common thermal bridge. We should try to minimize the degrading effects of thermal bridges. At walls, we can return insulation 12 to 18 inches, typically very easily, and neutralize the thermal bridge, as shown in this diagram. At floors, it can be architecturally more difficult to add insulation. If significant and pervasive thermal bridges cannot be eliminated, it may be appropriate, even if you can install very high amounts of insulation safely, to moderate the level of insulation, as the short-circuiting caused by the thermal bridges will cut the utility of such high levels. The goal is not simply to put as much insulation as humanly possible, but as much that is safe and makes sense. We're not lunatics, and it's another reason why airtightness is king. A potentially bigger problem than masonry thermal bridges are those locations where wood joists or beams sit in cold exterior walls. The image on top has the wood joist end heated dry with traditionally warm masonry. As we add insulation, as in the image at the bottom, the end of the joists get colder and potentially wetter. The biggest threat here is air leakage from the interior, as we discussed earlier. Air sealing the joist penetrations at exterior walls is critical. Here is a great example of floor joist penetrations being sealed by taping them to the INTELLO Plus interior vapor and air control membrane. Thermally broken beam connections are also an option. Other options include cutting beams back and attaching them indirectly, as shown here. Or one could build a building within the building, decoupling it from the masonry shell, allowing insulation levels to go as high as you'd like without worry. With water shedding, airtightness and vapor control, and robust thermal bridge-free insulation, the enclosure is ready to deliver comfort and efficiency. But there are still big holes in the high-performance enclosure. Don't undermine all this effort with mediocre windows and doors. Install great ones instead. Great windows that are fully integrated and continuous with the insulation and airtightness layers delivers great daylighting, comfort, and passive heating. They are no longer a detriment to the building performance, but enhance it greatly. And today there are a growing number of window options, and the price keeps dropping each year, making them affordable. And after many years of tweaking, there are not only historically appropriate simulated double-hung windows, where a fixed sash on top sits proud of a tilt-turn sash below, mimicking the profile of a traditional double-hung window, but 475 is proud to now offer the first Passive House Institute certified simulated double-hung window by BYSO for the best possible performance. Here's a page from our free downloadable ebook on the subject, explicitly calling out the components and their arrangement that make a fully integrated installation possible. You've got a great wall and you've got a great window. It needs to be installed properly to close the loop and get the benefits of continuity. With the enclosure optimized, finally it is important to provide great ventilation. As the saying goes, traditional exhaust-only systems mostly just suck. There's very little control, and the air quality from space to space can be highly variable. Great ventilation means providing distributed and balanced ventilation that has a high level of heat recovery. With such systems, the ventilation can be very low volume, where continuous fresh air is provided very close to room temperature without heating or cooling it. Ducted centralized systems are very common. Here, we see the air handler unit in the cellar with fresh air intake and ducted supply air to the bedrooms and living spaces, and exhaust air coming from the bathrooms and kitchens, going through a counterflow heat exchanger. 475 is pleased to provide decentralized options by Lunos, a ductless through-wall system that pulses fresh air in and stale air out with high-efficiency heat recovery. The E2 operates with 2 remote fans operating in synchronicity with each other, or the Ego, where the 2 fans are combined into a single tube, ideal for bathroom applications. And just coming to market, now we are happy to offer a semi-decentralized system, the Lunos Next, a through-wall unit that ventilates the room it is in, but also allows for exhaust and supply duct connections for a bathroom and bedroom. So with the ventilation component in place, we really have completed a high-performance historic masonry retrofit. Let's take a look at some examples. We'll look at a handful of details from a number of historic retrofits in Brooklyn, New York. All have either hit or are very near to Passive House performance levels. At the cellar, we see growing use of mineral wool insulation subslab, particularly since Roxol recently blessed the use of its IS board for such applications. On the left is a detail of the mineral wool turning up the masonry party wall to avoid thermal bridging from the ground. Here we see the blue poly subslab vapor and air barrier poking out around the perimeter. It is connected and made continuous with the masonry walls, which serve as an air barrier, with a felt Contiga Solido SL tape by Proclima. The wall slab connections can move, surfaces are porous, and we don't want components to embrittle or dry over time. Contiga HF acrylic caulking can provide that assurance. At the floor intersections, with the subfloor cut back, the air and vapor control membrane can extend continuously, as you see on the right, looking up at the subfloor with the INTELLO Plus shooting by. If joists sit too close to the wall, pull them away, repair the brick, and give room to this continuity. Again, we see the floor cut back. Again, it is critical to air seal beam penetrations, especially at exterior walls. Here's a high-performance window integrated with the INTELLO Plus. We can also see wood battens over the INTELLO Plus, which distribute the weight of dense pack insulation, but also create a service cavity for electrical and plumbing roughing. You can see the electrical boxes and wiring to the right. The service cavity protects the air and vapor control layer while dramatically reducing the number of penetrations through it. At the roof and wall connection, again, it is all about simplification and continuity, where we maintain the inboard air and vapor control between the wall and roof structures. As you can see in our ebook, it has a good deal of detail you can dive into. That's it. Simple, right? Well, for the moment, let's keep it simple. Let's successfully shed water. Let's maximize airtightness and vapor control. Let's maximize safe insulation levels. Let's install great and fully integrated windows. And let's install great balanced and distributed ventilation. We hope you dig into all this further with our free ebook, our free DWG files, and the many blog posts we have on the subject. Please don't hesitate to contact us. We enjoy reviewing drawings and details, helping optimize solutions, and helping you make the best building possible. We hope to hear from you soon. Have a good day, and thank you.